Right, topical subject, Lustre RAS. So, what is it we want? We want a file system that handles failure really well. A bit obvious, really. What does that mean? Well, when something fails, we want it to be functionally transparent, meaning that applications continue executing in spite of the failure, as if there had been no failure. And that whatever we had to do in order to overcome the failure has a minimal impact on, on the running of the system. So minimal performance impact. And really what that relies on is accurate diagnosis of failure, so that the right recovery actions are taken as soon as possible. That way we can minimize the performance impact. And that really means we have to have, in the Lustre context, in which our major strategies for dealing with failure are failover of servers and fail out of clients, is that we do it fast and we don't do it wrong. So we don't misdiagnose server failure or client failure. Now, we do have an issue with scalability, that we want to be able to scale to potentially hundreds of thousands of clients, thousands of servers. And the reason that's a problem, as Nathan alluded to, is that you get all those 100,000 clients lining up on a single server, and now your service latency has gone from X to 100,000X. So if your major diagnosis of failure is based on service latency, then having variance of 100,000X in your fundamental diagnostic technique is fraught with difficulty. And that's kind of where we are with Lustre. Also, don't forget the system administrator. We want to make it simple for a system administrator to set up a file system so that it doesn't continually misdiagnose failure and cause applications to abort when they didn't need to, for example. So how can we make this whole thing simpler? And obviously it needs to run a bit more automatically. Well, really what we would like to do is change our fundamental diagnostic of peer failure and stop relying so much on service latency and rely on something else. Wouldn't it be great if God could tell you, something's going on here, take evasive action? That's kind of what we're looking for. Now, clearly that doesn't exist, but there are much better ways of diagnosing peer failure than using service latency. One other thing to notice as well is that server service latency is dependent on disks. Disks are mechanical devices. They also have very unpredictable latency. So when a head misses its track, it resorts to some sort of algorithm to find, to reposition or recalibrate the head. That can also result in huge additional service latency. So networks are a bit easier than physical devices. They have a bit more predictable latency. Sure enough, if you inject huge numbers of packets into a network, then the latency of any individual packet crossing the network is going to increase. But if you can somehow control the total population of packets and size of packets in the network, then actually you can bound network latency. So what we'd like to do is make some sort of way of diagnosing peer failure based on, basically based on collectives, getting the nodes to help each other to diagnose failure rather than fighting all of each other all of the time to do the diagnostics independently. Something else that people have alluded to here is that Lustre was originally debugged at scale on networks that had no routers. Point to point, the underlying LNet implementation pretty well guaranteed that unless you had flaky hardware, if the hardware was working reasonably well, your point-to-point connections, the messages would not be dropped, and therefore message drop was not really a big factor in the original Lustre protocol design. Now, when we have router failures, or actually real networks really do have intermittent failures, then that starts to expose some of the weaknesses in the Lustre protocol. Now, Lustre recovery has got one big technique, which is, reestablish a new connection to my server and then, renegotiate everything, resend, replay, all that stuff. So I think really what we could do here is recognize that there are two different sorts of failure here. There is network failure, the failure of my communications to reach my peer across the network because of something that went wrong in the network. And therefore, we should try and cope with that with a fairly lightweight and fairly simple to retry and something you can try a bit more aggressively. Distinguish that from peer failure, where really now you're at the Lustre protocol level, and what you're trying to do is cope with things like server failover. So in the Fast Forward project, we kind of knew that these RAS issues were going to be a big deal in a disk-based file system that we were, that you want to grow to exascale. And that Lustre's current every man for himself way of dealing with RAS was not going to get there. Also, we knew, because we wanted to do distributed transactions, that we needed a way of doing scalable distributed communications. And so we needed two things in Fast Forward. One of them was scalable collective health monitoring, and another one was scalable collective imperatives. So the collective health monitoring that we did was based on this thing called gossip. Now, gossip really is kind of you can think of it as a non-deterministic KRE tree for distributing shared state throughout a cluster. Now, what does that mean? Okay, well, there's a cluster of all those blue nodes. The green node there is a node that's got some new information that it wants to share with its peers. And the gray nodes there are dead nodes. So we're assuming that there are going to be some dead nodes in the cluster and that we've got to have some way of routing around them. So what happens in gossip is that you randomly pick one peer to communicate with and update it. So look, we've gone from one node having something new to say to now two nodes know about it. In the next round of the gossip, they do the same thing again. They randomly pick two more nodes to share their information with and update them. That carries on. So actually, it doesn't really matter so much if you pick a node that either has the information already or is dead and isn't going to propagate it any further for you, because everybody else is doing this for you as well. So in roughly log n steps, you've actually propagated this new information that you had to every other node in the cluster. And it's non-deterministic, so it routes around failure, and it's actually very reliable. Now, when the information you want to share is a Lamport clock of how alive you are, that means that every other node in the cluster within log n steps, so let's say we've got 1,000 node server cluster, within roughly 10 steps, every other node in the server cluster is going to know how alive you are. So if the nodes start seeing that one particular one of their peers, that his Lamport clock isn't ticking any longer, that's going to be a fairly reliable indication that that node is not contributing Lamport clocks anymore. In other words, it's not playing the game, it's probably dead. So if we ensure that nodes do some sort of self-checking, And these are all server nodes or router nodes, but they're system nodes, they're not client nodes, so we can kind of depend on them to execute the protocol, in the spirit of the protocol. Then actually we can have quite reliable and accurate and low latency notification of peer health. So, each node is on average choosing one other node to share its information with. In something like in a 1,000-node cluster, that's only actually 1,000 bytes of Lamport clocks that you need to send to one peer. If you did that once a second, then within 10 seconds, you've propagated your Lamport clock to everybody else in the cluster. If you could afford to do that 10 times a second, within 1 second, your Lamport clock would be distributed to everyone. That's pretty low latency. Oh, and so what I should say is that in the prototype that we implemented this general API so that you can query any other node status and register callbacks for when peer node status changes. So that's all very well. That means the servers and the routers can all keep each other up to date on, how healthy they are. But what happens if I want to share information with all the other nodes in the server cluster, such as here's a new client, and I think this client is healthy. If I want to distribute that information, I don't want to do it point to point with all my other servers. Otherwise, I'll be sending 1,000 messages. Again, I want to do this on a tree, but this time I can do it on a deterministic tree. So when I know all of my peer servers, I can just assign them a unique index in a dense array. That unique index can be used to determine a k-array tree topology, which is what we see on the top right there. And that topology can then be used to distribute this information. Now, the 0th node is the root of the tree. It can actually send the information about who are the other members in the tree in the initial request. And so you can propagate a request down through the tree, which steers itself to all of the relevant places and can collect a result all the way back. Now, we've implemented something actually very general purpose with callbacks at every stage of the communication so that we can do MPI-style reductions, for example. We can say, do a query to all of the servers, what do you know about X or Y, and then have them all contribute their information, and then if that information can be combined somehow to compress it, then you can do that at each stage. We can even do bulk RPCs with this. If you register bulk buffers, we could either register a single bulk buffer at the root of the tree and then have every member of the tree slot their contribution to the bulk result into that bulk buffer, or we can do the same sort of thing of combining and reducing on the way up. So it's very, very general purpose. Okay, so we've got these two new facilities ready to roll with Lustre. Now, before we start using them to leverage improved RAS, let's just go through some details. First of all, in the Lustre protocol, we have a number of RPC steps. Now, the client, or typically the client, in the case of lock callbacks, it's reversed, but for everything else, when the client sends an RPC to the server, it consists of a number of steps. The only effectively unsolicited action, the only thing that can deluge the server with huge numbers of messages outside of its control effectively, is the RPC request. After the RPC request gets sent, everything else happens under control of the server. That's actually why Lustre has good congestion properties on networks, because even though every node in a 20,000 node cluster is maybe wanting to do megabyte RPCs, they don't send the megabyte in their initial request In fact, they queue up probably 8 of them at once because they want to keep 8 on the wire to do pipelining. But these requests, they're tiny. They traverse the network with very low latency, they arrive at the server, and they're buffered. Now, it does mean that the server now has quite a deep queue, yeah? But the network latency, the time to traverse the network, was well bounded. 20,000 RPC requests of a few K each on point-to-point links that are capable of doing gigabytes per second. That's not a long time on the wire. Now, once the RPC request is there at the server, now it's the server concurrency that determines the number of bulk messages that might all be converging on the server at once. So if I want to limit the maximum latency across my network, I can first of all say clients should be limited to some maximum number of small RPC requests. This is why RPC requests that can grow to hundreds of K are an anathema. They will destabilize our ability to predict network latency. So we want to keep all RPC requests nice and short. We also want to limit the number of concurrent bulks on the wire on each server. If we do that, we can bound the network latency within fairly tight limits. Unlike service latency, where we're dependent on physical disks and where we need to keep many, many, many concurrent IOs in flight to our disks, network latency can be much better bounded than service latencies. So the other assumption we want to make is that really the network does work pretty well most of the time. Maybe not 100% of the time, but we don't really want to see more than 1 in 1,000 messages getting dropped, say. If that's the case, we really have got something really too flaky in the network. But we definitely want to be robust against that kind of level of repeated failures. So, what are we going to do? Well, let's make the Lustre servers and routers responsible for monitoring their own health. We can do that very scalably using gossip, and we can get very, very low latency. And we can use, in addition, we can do stuff like have the routers monitor themselves for asymmetric failure, for example, so that they stop broadcasting their Lamport clock of liveness when they diagnose some failure within themselves. We can have servers do similar sorts of things. But if we were to gossip at, say, 4 times a second, if we had, even if we're gossiping for every single storage target in the machine, if we have like 10,000 storage targets in our server cluster, an additional 1,000 routers, actually the gossip vector here is not very large. There's very minimal network overhead. And with very sort of safe assumptions about what the propagation latency is, we could probably have notification within 15 seconds or so of a router failure or a server failure. The next thing we want to do is monitor our clients. Now, the reason that pings were first added into Lustre was because we found that we were getting sequential timeouts occurring. So a server would diagnose that a particular client was dead because for example, it wasn't responding to lock callbacks. It would wait. It would then time out the client and progress to the next I/O, and then discover that another I/O on a different client now was this different client was not being responsive. And so we needed a way of ensuring that when a whole bunch of clients all become responsive at roughly the same time, that they're all timed out together rather than timed out sequentially. Now, that's where the n-squared pinging started. Of course, by the time we get to the number of servers or OSTs, actually the pinging is per OST, by the time we get to the number of OSTs that on something like the K machine, it's completely out to lunch. We have these ping storms. Now, we still need to have some way of getting prompt notification when clients are dead. But rather than having it all done independently on each client, a much more scalable way of doing that would be to have to split the clients up over all of the servers. So in that way, we can reduce the ping load on any individual server proportional to the number of servers. So we can reduce that by a factor of 1,000. In addition, the individual servers could be a bit smarter about diagnosing client health. Now, that means that we've got individual servers with a good idea of the state of client health of particular clients, but they need to share that information with the rest of the cluster somehow. And therefore, what we need to do is some sort of periodic collective, and we've got the infrastructure for doing these scalable collectives, which share the information about which clients are live and which clients are dead. And we really want to do that periodically. We don't want it to be event-driven by client actions, because then clients could start re-registering with lots of different servers, for example, if they weren't playing the game. You can't trust clients to the same extent that you can trust servers. But these collectives then, they can be sure that in each stage of the collective, you can aggregate and merge the information from all of the servers that are monitoring all of the clients to ensure that the whole collective occurs scalably and with reasonably low overhead. And in fact, in normal systems, clients aren't, new clients aren't starting and clients aren't dying, all the time. Or if they are, it's not all of your client cluster suddenly goes, starts up and then crashes and then starts up and then crashes and then starts up. And that's a major thing. It's not going to happen all the time. And therefore, you could assume that that most of the time, client status is going to stay the same, and you can optimize for that. So these collectives that share information about client status, can actually have very, very low overhead most of the time, and it's only when clients boot and crash that actually there's a bit more overhead. So if we have up-to-date information about client status and server status, how are we going to use that to make Lustre communications more reliable? Well, I would suggest that what we should do is that for every step of an RPC, the request from the client, any bulk that the server conducts, and the reply from the client, from the server back to the client, make them round trip. At the moment, they're not all round trip. Some of them are. Some of the RPC replies, for example, some of them are round trip. There's an ACK that says the client actually received the reply, and we use that to help us with recovery, for Lustre level recovery. But we could use that for network style recovery. We know that we can bound network latency much more tightly than we can service latency, and therefore not getting an ACK from your initial RPC request, within a few seconds, is a good indication that the network has dropped your request, and therefore you should send another. Now, clearly you don't want to do that on too much of a hair trigger, because there lies the possibility of a congestion. But if we were to say, look, we're going to routinely resend RPC requests, within 20 seconds, say, that's not going to create an excessive congestion problem, but it is going to be a lot more. It is going to allow us to deal with very intermittent network errors much more successfully. Now, that does mean that we have to change some of the way that we do the protocol. So when our RPCs arrive at the server, we'd have to make sure that we can just discard duplicates. So we'd have to have a reliable way of detecting duplicates and discarding them. We already do that in some ways, but so it'd be fairly simple to add. Similarly, when the server replies or runs bulk, we have to make sure that if the reply really did get there, but the ACK was lost, that we can resend the reply and get another ACK to confirm to the server that the reply really did get there properly. But with these fairly minor changes, we could get away from these adaptive timeouts, which are currently, quite a major source of code complexity in the RPC layer, and a major source of bugs as we implement different recovery and diagnostic. So with that, primarily using notifications from the health network of router failures, for example, that would let us route around crashing routers very aggressively, and back off to a simple fixed timeout for normal network recovery. That means that the harder task then of peer recovery, we're doing the more complicated Lustre recovery, and we can have much more expanded, much more conservative timeouts that can act as catch-all in the case where we were unable to get prompt notification of peer death. Most of the time, we will get prompt notification of peer death because we can monitor our clients very effectively, and certainly our servers who can also be doing their own self-diagnostics. So most of the time, we'll get a very, within 10, 15 seconds or so, we'll get prompt notification of peer server or client death. We can give that to the clients as well, so that clients get prompt notification and can attempt failover, for example, which is a somewhat more scalable way of doing imperative recovery than maybe the way we do it today. Another major benefit of this is that because we have collective notification of client health, we can also do collective eviction of clients. And this enables additional features that have been on hold, because we don't have that sort of guarantee. So being able to cache the size of a file on the metadata server is something that could really improve file stat. It would eliminate a huge source of traffic and additional network round trips when you're listing files in a directory, for example. We can't do it today because all the servers act completely independently and evict clients independently, and therefore, when the MDS decides to evict a client, it doesn't know whether the client is still writing to the OST objects of a file. And therefore, that just means that you can't cache any attributes derived from OST objects on the metadata server. So having something like global client eviction, could enable much more improved Lustre features. So finally, what we'd like to do is leverage the collectives, the gossip, and the imperative collectives that we developed in Fast Forward to change the way to do much more scalable health monitoring within Lustre. To change Lustre recovery to make it a two-stage thing to separate network recovery, where latencies can be well bounded and retry is very simple, from end-to-end recovery, peer recovery, which does the full Lustre recovery protocol. And the simplified network recovery would be predicated on being able to do these simple network round-trip handshakes for each stage of the RPC. Right, any questions?
Plenty of questions.
My question is regarding the node failure you have mentioned in the beginning, the first half of the presentation, where we're talking of any node failure. So do we consider it as a part of reliability or availability? Because when the node, or since in Lustre we have HA at all the places, at all levels, network level, node level, so that means the Lustre is never going to fail. It's only that your performance may get reduced, and by having this collecting mechanism, probably you are reducing the time. By the time you will be able to, the client can resume its operation again. So am I correct in my understanding? First of all, I'd like to know, because I think it's more of a problem of availability than the reliability.
So, well, yes, indeed. Availability, we could cut down the latency to knowing that something has gone wrong.
So basically, we in the modeling domain, we call it as a performability, that what will be the performance of the system, Lustre system, when something goes down.
Indeed, indeed. And it would avoid today's problem of, the system is basically completely passive for many minutes at a time until finally, excuse me, service latency-based diagnostics come into effect. The other major effect, though, is a reliability effect, which is the huge complication of some of the timeout and protocol recovery code that exists today. And by stripping out, for example, adaptive timeouts, which would no longer really be necessary, we could make the code itself simpler to understand and therefore maintain. We would reduce a huge source of bugs and then make Lustre as a whole more reliable as a result.
Okay. And another question, I just need to understand, what is the mean time today, whatever Lustre versions we have available, what is the mean time to detect the failure in the system? And how much time does it take to come back? I know the client is transparent to that. Just for my understanding purpose, I need to know how much time does it take to detect any failure of the node, and how much time does it take to come back?
So that's a hard question to answer today, because these diagnostics are based on service latency. And so whatever the site-wide AT max is currently set to, that's the kind of the big multiplier. Because, for fairly trivial single client, most clients are passive, single clients are active. At that point, the service latency is well bounded, and AT kind of adapts to that. But Lustre actually is all about coherent load and congestion, and therefore that's the effect of that is just to mean that you're always operating at congested, large service latencies. And so, 300 seconds or so, is kind of where we are today. That's far too long to leave a cluster idle because one message got dropped somewhere.
Thank you.